All right, in this video, we're going to look at question 4, part A. It says to compute the Jacobian for each of the transformations in problems 2 and 3. Okay, so we've now looked at a number of various transformations, and in the last video, we defined the Jacobian of a transformation. So to recall, let's say I have x and y as functions of u and v, and these define our transformation t. The Jacobian of this transformation is the determinant of this 2 by 2 matrix. It's made up of these partial derivatives of x and y with respect to u and v. And this determinant is telling us this area distortion factor when comparing the area of a small region here in the UV plane to the area of its image over here in the XY plane. Okay, so to illustrate, let's go ahead and look at the transformation from problem 2, part A, where x is 2u and y is 2v. So the Jacobian here, this is going to be the determinant of the following matrix, right? I want the u derivative of x, that's going to be 2. And then I want the v derivative of x, that'd be 0 because x is independent of v. Then I want the u derivative of y, and that's going to be 0. And then I want the v derivative of y, and that's going to be 2. Okay, so I'm going to get 2 times 2 minus 0 times 0. That's going to give me a Jacobian of 4. Okay, so what does this tell us? Well, it tells us that this transformation t scales area by a factor of 4. And you can see that here with the unit square. This has area 1, and its image here has area 4. And that also makes sense just given the fact that this transformation t dilates horizontally by a factor of 2 as well as vertically by a factor of 2. So as a consequence of that, we're going to get a dilation factor for area that's equal to 4. All right, cool. So then for 2b, x is 2u and y is 4u plus v. Okay, so go ahead and compute the Jacobian here. So the u derivative of x, that'd be 2. The v derivative would be 0. And then for y, we have the u derivative, that'd be 4, and the v derivative would be 1. And this determinant would be 2 times 1 minus 4 times 0, and that's just going to be 2. Okay, so this is telling us that this transformation scales area by a factor of 2. And recall that this transformation mapped the unit square to this parallelogram, and you can easily check that the area of this parallelogram is in fact 2. All right, for 2c, we have x is u minus v over the root of 2, and y is u plus v all over the root of 2. So for the Jacobian, we're looking at this determinant. So the u derivative of x would be 1 over root 2, and the v derivative of x would be minus 1 over root 2. The u derivative of y, that'd be 1 over root 2, and the v derivative of y is also 1 over root 2. Okay, so now I have 1 over root 2 times itself, so that's a half, and then minus a minus, so careful there, so for the plus a half, so a half plus a half is going to give us a determinant of 1. Okay, so what does this say? Well, it says that this transformation does not distort areas. Okay, and recall what this transformation did. It just rotated this unit square counterclockwise by 45 degrees, and that certainly will not distort area. Okay, if you've taken linear algebra, you might recognize this as a rotation matrix. That's exactly what T is. Okay, T is a rotation of 45 degrees counterclockwise about the origin. All right, cool. So now let's go ahead and look at the transformations for problem 3. Now, part A is so similar to 2A. I've just done it here already. So x is 2u and y is 4v, and we get this Jacobian of 8. And recall that this transformation mapped the unit disk in the UV plane over to this region bounded by this ellipse in the XY plane. And so the fact that this transformation is stretching horizontally by a factor of 2 and stretching vertically by a factor of 4, is giving rise to this area distortion factor of 8. Okay, that makes sense. All right, for 3b, now a little bit more complicated here. We go ahead and take the u derivative of x. That's going to give us 1 minus v. Then take the v derivative of x, and that's going to give us minus u. Then take the u derivative of y, and that's going to be v. And then take the v derivative of y, and that's going to give us u. All right, so we get 1 minus v times u. There's that product. And then minus u times v. So let's clean this up a little bit. We're going to get u minus uv, and then this is plus uv. So those are going to drop out, which is nice. And that simplifies to u. Okay, so this is the first example we've seen where the Jacobian is not constant. And so the fact that the Jacobian comes out to be u would imply that if I were to, say, look at a little region over here versus, say, a comparable region over here. So they have the same area, but this one is just further to the right than this one. Well, if I look at their images, okay, the image of this region off to the right will be distorted to a greater degree, right? Because the distortion factor here is given by u. And if we're off to the right here, right, the u values for these points are greater than the u values for these points. So that would be a consequence of this. So we have non-uniform area distortion for this map. And this u is the expression that tells us what that distortion is. Okay, so now lastly, 3c. All right, we'll go ahead and compute following determinants. So the u derivative of x, that'd be 2u. The v derivative be minus 2v. For the y derivatives, we're going to get for the, let's see, the u derivative of y, this is going to be minus 2v. And then for the v derivative, that'd be minus 2u. And so here we're looking at minus 4u squared, and then minus, because it's here it's a negative times a negative, so it really is a minus 4v squared. And I'll write that as minus 4 times the quantity u squared plus v squared. Okay, so the fact that this comes out to be a negative quantity, aside from at this one single point at the origin, but aside from that, this will be negative. So what is that telling us in terms of area distortion? Well, let's say it comes out to be, say, negative 8. Okay, well, it's still saying that this transformation is going to scale area by a factor of 8, but the negative is now due to what's known as an orientation reversal. So like, let's say I have a little circle here that rotates around, say, counterclockwise in the UV plane. When it's going to get mapped over here, this orientation reversal is going to rotate this image, the image circle will rotate now clockwise as opposed to counterclockwise. Okay, so there's, of course, a lot more to that story, and I'm not going to get into it because it won't be terribly important for us, but I did want to just point that out. But yeah, that's going to do it for this question. In the next video, we'll look at the Jacobian related to polar coordinates. All right, see you there.